Hello, everyone, and welcome to our 10th numerical analysis lecture. This will be our last one this summer. And what we're going to talk about today is Euler's method for solving a first-order linear differential equation. And first, we're going to look at the geometric approach. Here's the application. What we want to do is approximate the solution of a first-order linear differential equation of the form y prime equals some function in terms of x and y, or some expression in terms of x and y. And the solution is essentially the function y evaluated at whatever x value we want it evaluated at. The solution of this equation y is defined on the interval from x equal a to x equal b, and it's subject to the initial condition that y evaluated at a is equal to alpha. So in other words, we have an initial condition. We know the value of the solution at x equal a. What we're looking for and what we consider to be the solution of this equation is the function y evaluated at x equal b. In other words, we know the value of y at x equal a, and what we're looking for is the value of y at the other endpoint. So what we're looking for is the function y evaluated at b. And this is going to be a number. We want the value of y evaluated at b. Now, a little bit more on equations of this form. Y prime equals some function f of both x and y. And here are some things that here are equations of the type that we're talking about here. Y equals some function of both x and y. And we could have, for example, y prime equals y squared plus 1 over x. So this is going to be our function of x and y. Another example, y prime equals, let's say, negative 2y plus 1 over 1 plus e to the 4x, let's say that. So here is our function f of xy. And these are examples of the kinds of differential equations that we might want to solve using Euler's method. Here's part of the basic idea of our algorithm. Geometrically, Euler's method is based on the assumption that the graph of a function y of x can be approximated by many small line segments, as shown below. And here's the graph of y equals y of x. And here's our approximation of the graph of y equals y of x. Notice essentially they're about the same shape, except our approximation of y of x is formed by taking a bunch of line segments and putting them end to end together. But essentially, the shape of this graph is the same as the shape of that graph, except this one is not smooth. It's made up of a bunch of line segments. Okay, we'll elaborate on this a little bit further. Given a known point on the graph of y equals y of x, and let's say that the coordinates of that known point are x sub I and y evaluated at x sub I. Given that this is a known point, we can approximate the y coordinate of another point on the graph that's close by, and we'll call that neighboring point on the graph x sub I plus 1 and y evaluated at x sub I plus 1. So let's do this again. Given a known point on the graph of y equals y of x, and let's say the known point is x sub I, y evaluated at x sub I, we can approximate the y coordinate of another point, a neighboring point, x sub I plus 1 and y evaluated at x sub I plus 1. Here it is down here. Here's x sub I, y evaluated at x sub I, the known point. Here's x sub I plus 1, y evaluated at x sub I plus 1. And we want to approximate the y value of that point. And we're told that we can approximate the y coordinate of this point by traveling along the line tangent to the graph at the point x sub I, y evaluated at x sub I, until we reach the x coordinate x sub I plus 1. So here's the scoop. And do I have a blue marker? I must. Here's a tangent or a line tangent to the graph at the point x sub I, y evaluated at x sub I. We're looking for the y coordinate of a neighboring point on the graph, y evaluated at x sub I plus 1. So what we do, since we have this known point, is draw a tangent to the graph at the point x sub I, y x sub I, and we travel along the tangent. We travel along the tangent until we reach the x coordinate x sub I plus 1. So we travel along this tangent until we reach x sub I plus 1. And guess what? The y coordinate of this point on the tangent is going to be our approximation for the y coordinate on the graph of y equals y of x. we have a known point on the graph, x sub I, y evaluated at x sub I. We have an unknown point on the graph, x sub I plus 1, y evaluated at x sub I plus 1. We want to approximate the y coordinate at this point, and here's what we do. We start at the point, the known point, x sub I, y evaluated at x sub I, and we travel along the tangent line until we reach the x coordinate, x sub I plus 1. And the y coordinate of this point on the tangent is going to be our approximation to the y coordinate on the graph of y equals y of x. And can we find this point? Can we find the y coordinate at this point? Apparently we can. That's our scheme. That's what we're up to. How we're going to find the y coordinate of this point on the tangent line is coming up next. Before I erase this picture, let me make one or two more comments. I'm going to call the y coordinate of this point on the tangent y sub I plus 1. So y sub I plus 1 is our approximation to y evaluated at x sub I plus 1. And one other thing, when we start at the point of tangency and move along the tangent until we reach x sub I plus 1, we call this process shooting the arrow. And I may talk a little bit more about that in just a second. If we have a curve that's concave down, it's a little bit more natural for me to explain it. So as far as shooting the arrow goes, I'll talk about that in a minute. How do we get the value of y sub I plus 1? That's the y coordinate of this point, as an approximation to y evaluated at x sub I plus 1, which is the y coordinate of that point. How do we get the y coordinate of this point? We use the slope formula. y2 minus y1 over x2 minus x1. In terms of our points xi, yi, and x sub I plus 1, y sub I plus 1, we have, and I stop for a minute and say, wait a minute, we have x sub I, y sub I? But we have x sub I, y evaluated at x sub I. How do I get y sub I? Well, here's the thing. We're letting y sub I plus 1 be the y coordinate of a point on the tangent. Well, here, the tangent and the point on the graph have a point in common. At x equal x sub I, the y coordinate of the tangent and the y coordinate of the point on the graph are one and the same. So, x sub I, y sub I, and y sub I and y evaluated at x sub I are exactly the same value. So technically this is also y evaluated at x sub I. They are one and the same thing. So our slope is y prime evaluated at x sub I, the slope of the tangent. And this is how we get, but we're going to solve this for y evaluated, for y sub I plus 1. Now, if we're going to solve this equation for y sub I plus 1, I guess that means that somehow we have to know what y prime evaluated at x sub I is. And in fact, we do, and here's why. Remember, y prime is some function evaluated at xy. So y prime evaluated at x sub I is f evaluated at x sub I, y sub I. And we know what x sub I is. And we know what y sub I is because y sub I is the same as y evaluated at x sub I. And these are the coordinates of a known point on the graph. We know the x and y coordinates at this point. So yeah, this is something that we can compute. The only unknown here is going to be y sub I plus 1, and we can solve for that. Recall that we're going to solve this equation for y sub I plus 1. And we have the slope, y prime evaluated at x sub I equal to y sub I plus 1 minus y sub I over x sub I plus 1 minus x sub I. And we're going to solve this equation for y sub I plus 1. So we multiply both sides by the denominator. And then we move y sub I over to this side of the equation. And then we just switch sides of the equation to get y sub I plus 1 on the left. And there's one more modification we're going to make, and that's for y prime evaluated at x sub I. Remember, our differential equation is of the form y prime equals some function of both x and y. So we're going to replace this y prime evaluated at x sub I by f evaluated at x sub I and y sub I. So this thing is replaced by this thing. And let's just keep this for a moment. There's one more revision I'm going to make on this, but for right now, this is the form of our equation that we're going to use to approximate successive values of y. Given y sub I, given that we know y sub I, we're going to use this equation to generate successive values of y sub I plus 1. So here's how we apply all of this. We have the equation y prime equals f evaluated in x and y. In other words, y prime is some function of x and y. We know that y evaluated at a is alpha. So we know the value of y of a. We want the value of y evaluated at b. Here's what we want. That's what we want. here we have A, y evaluated at A. That's the same as A alpha. And we're going to use the scheme that we just developed to work from here to here. And this is how we're going to do it. Specifically, here's how we do it. That we partition the interval from A to B into n subintervals of length h equals b minus a over n. So h is essentially our delta x here. And we've got the interval from A to B partitioned into n subintervals. A is equal to x of naught. B is equal to x of n. And every subinterval has width h. So that's our first order of business. Partition the whole interval into n subintervals of length h. And guess what we're going to do? Let's see, by the way, y of x of naught is going to be the same as y evaluated at x of naught. Because this is a point on the graph of y equals y of x, it's also a point on our tangent line. So the y coordinate of this point is y sub naught, same as y evaluated at x of naught. And that's going to be alpha. The coordinates of this point are going to be x1, y1, and how do we compute y1? Let's see. In general, for I equal 1, 2, n, y sub I plus 1 is equal to y sub I plus f evaluated at x sub I, y sub I. And we have x sub I plus 1 minus x sub I that we want to scrunch in here. But x sub I plus 1 minus x sub I is just h. So we can modify this thing and replace this expression with h. This is how we're going to successively, or this is how we're going to generate successive values of I, y sub I plus 1. Given x sub 0, y sub 0, where y sub 0 is alpha, we generate x sub 1, y sub 1. And then what we do from this point is we shoot another arrow that's parallel to the tangent. We shoot another arrow that's parallel to the tangent at x equal 1. We're going to let y sub 1 be essentially the known value that we're working with to get y sub 2. And now we're going to shoot an arrow that's parallel to the tangent at this point. Whoops. And then when we get this, we're going to shoot an arrow that's parallel to the tangent at this point. And when we get these coordinates, we're going to shoot an arrow that's parallel to the tangent at this point. And so on and so forth. And this point right here will be x sub n, y sub n, or b, y of b, approximately. So our y sub n is going to be approximately equal to y evaluated at b, which is the solution to our differential equation. We're going to derive the algorithm that we just saw, but we're going to do it a different way. This is the Taylor series approach. Our objective is still to approximate the solutions of first-order linear differential equations of the form y prime equals some function of both x and y on the interval AB, subject to the initial condition y evaluated at a equals alpha. In other words, we know the value of our function y at x equal a. The solution that we seek is the value of y at the other end point, b. And here's what we do. We consider the Taylor series expansion of y of x about the center x of naught. And we have y of x equals y evaluated at x of naught, y prime evaluated at x of naught times x minus x naught, y double prime evaluated at x naught times x minus x naught squared over 2, and so forth and so on. And now we're going to introduce h. Let h equal x minus x naught. Then this is what we get for y evaluated at x. Y evaluated at x naught plus y prime evaluated at x naught h plus y double prime evaluated at x naught times h squared over 2 plus dot 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 nth derivative of y evaluated at x of naught times h to the n over n factorial, so on and so forth. Before I completely erase what I had, I want to draw attention to something. This line's fine. And we said, let h equal x minus x naught. And so x minus x naught became h, and so on and so forth. Well, there's one other thing I should have changed here. If h equals x minus x naught, if I add x naught to both sides, I get x naught plus h equals x. And so this y evaluated at x really should be y evaluated at x naught plus h. So the last line should have been y evaluated at x naught plus h. I wanted to write it in terms of x naught and h and get rid of all of my x's, so I needed to get rid of the x here. Continuing, if h is small, then our equation becomes, well, what does it become? Let's see. If h is small, then h squared is going to be really small, and h to the n over n factorial is going to be really, 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 really small. If h is small, these terms are going to be very small, and we can just lump them together and throw them away. So our equation is going to become y evaluated at x naught plus h is approximately equal to y naught, no, let's see, y evaluated at x naught plus y prime evaluated at x naught times h. If h is really small, then essentially this is what y evaluated at x of naught plus h is going to look like. If h is small, we can throw away all the terms except for these two on the right side. And that's a good approximation for y evaluated at x of naught plus h. And we're going to take this relationship and apply it to our problem. The first thing we do is we partition the interval AB into n subintervals of length h, where h is b minus a over n. And we define x of naught to be a, and we define y sub naught to be alpha. Remember, y evaluated at a is equal to alpha, so this is just our initial condition. And for I equal 1 through n, we define x sub I to be x sub I minus 1 plus h. Or I guess another way of putting it, x sub I plus 1 equals x sub I plus h. No, I'll tell you what. For I equal to 0, 1, 2, to n minus 1, there we go. We define x sub I plus 1 to equal x sub I plus h. So when I is 0, x sub 1 is equal to x sub 0 plus h. When I is n minus 1, x sub I plus 1 is x sub n, and that's equal to x sub n minus 1 plus h. Okay, I like that. And we define y sub I to be y evaluated at x sub I. This equation, by the way, I labeled equation 1. So I guess I can say this. I love this expression. Proceeding inductively, equation 1 becomes y evaluated at, what would I say, x of I plus h equals y evaluated at x of I plus y prime evaluated at x of I times h. So just put x of I in here, x of I, x of I. That looks good. So then this means that y sub I plus 1, now y of x of I plus 1 equals y of x of I plus y prime x of 1 times h. And x of I plus y evaluated at x of I plus 1, we're letting that just be y sub I plus 1. Let me erase some board. We left off right here. And I want to rewrite this y prime of x of I as something else. Y prime, that's f evaluated at x and y. So y sub I plus 1 is equal to approximately y sub I plus f of x sub I, y sub I times h. And we generate all of our y's this way. And our solution, y evaluated at b, is equal to y sub n. And that's the Taylor series approach to doing the Euler's method for solving first order linear differential equations.